today I'd like to introduce about my work that we published last year, which is called DIB-X, Formulating Explainability Principles for a Self-Explainable Model through Information Theoretic Learning. So this talk has basically 4 sections. I would like to briefly introduce about self-explainable models for images. And here only discuss, we only consider explanation as a salience map. And the second, we try to answer to the question, what constitutes a good explanation with respect to learning saliency maps? And then our framework, DIB-X, will be introduced in the next. And then finally, I want to share some result from our application research, which is called Visually Explainable Document Question Answering. So what are the explainable models? So in this book, very famous book, the main definition is that explainable models should provide a human understandable reasoning or justification for their decisions. And then my question is, what are the explainable models for images? So based on this definition, I just picked 2 keywords from one decision, the other human understandable reasoning. But the decision part is relatively easy to understand or very intuitive because we already have a well-established image-based downstream task. For example, image classification, object detection, semantic segmentation, and so on. But when it comes to human understandable stuff, it's a bit difficult to get some very concrete intuition because it still encompasses a broad interpretation. And in this field, for the image dataset, one common approach is to create saliency maps, and which highlight the regions that align with this model's decision. And this presentation is limited to the saliency map-based explanation. Okay, then how we can create the saliency maps? So basically, we visualize the output-input relevance from the trained and frozen network. This is often called post-explainable method for images. So hopefully this figure helps to have some understanding of this. So we have a neural network, and we are going to train the neural network. For example, this MNIST number 5 images, MNIST data, to have some prediction, 5. And we want the model to learn to achieve a good accuracy. So we just include some good accuracy related terms, loss terms into this objective function. Yeah, cross entropy, for example. And then what we do is to freeze the network. So we don't change anything. And then we just try to, let's say, stimulate a bit from this output to input or some other directions, try to get those sort of heat map like saliency map that saying that this is sort of the most relevant region in the input with respect to the output. So based on this, there are many different postdoc methods. I just brought a figure showing some of them, all based on this gradient based. And these are the original input, and there are the corresponding classes. So when we just simply visualize the gradient, it's like a very, very foggy, cloudy, I don't even know what it is. And the new different methods can sharpen a little bit. But this, so up to this, they are something related to neural network. But this edge detector, it does not use any neural network, but it just extract some edges directly to the input. But still, it's a very natural. I mean, it says something. And when we see this edge detector result, and then we start to doubt about those postdoc explainability method, because then we start to confuse. We start to get confused. What is then good explanation? So in fact, when it comes to neural network, and then when we use the gradient backpropagating from the output to the input, And then in the end, what highlight the input level is just a low-level representation of this gradient, and that often exhibit these characteristics similar to those on the edge detector result. So motivation. So within the salience map explanation, do the postdoc method truly provide meaningful explanations? And are they only highlighting low-level features of the images, such as edges, without offering any deeper insights? And then, would directly learning this salience map as a form of representation lead to the more robust and intrinsic explanations? So this is sort of the last one is about the core idea about self-explainability. So here we want to learn the salience maps, not using the trained and the frozen network to find the relevance. So here this figure contrasts those two things. The upper one related to postdoc explainability, the lower one related to self-explainability. So here we have the same input, hopefully same network, but slightly different. But in the end, we want to have those two. We want to have this prediction and also its explanation. So it's we observe in upper cases in order to make good prediction. The objective function should include the term related to the good accuracy term. So we want to achieve this. But what we also want to have a good explanation as well. And that naturally we need some good explainability requirement, which plays like an accuracy for prediction. And then when we need to formulate those explanatory requirements and put into the objective function so that this neural network can learn, considering this all objective during training. So here, this explainability requirements are the criteria for the effective explanation based on the definition, which is decision-related, also human understandable reasoning. Here, and for this human understandable reasoning, we need a bit of a philosophical thinking, reflecting the broader notion of intelligence. And actually, there are many philosophical so-called concepts, for example, or principles. For example, simplicity, faithfulness, completeness, transparency, ethical consideration for language models, or domestic specific requirement, and so on. And if you want to know a little bit about this philosophical foundation, I recommend you to have a look at this paper. It's quite well illustrated. But then, okay, how we can just incorporate this requirement into the learning system? And what we propose here, so-called DIB-X, deterministic information bottleneck explainability, is to mathematically formulate this each requirement. We actually picked 3 requirements to a single loss term, each loss term. And then we incorporate into the objective function and then train end-to-end within a single downstream test. So we are not doing this multiple downstream test, but we are only predicting this single one, but we want to have it in the meantime, so that we can say that this explanation is also part of this prediction. So yes, so our method DIB-X is aim is to learn this salience maps and this elements with explanations as a part of this model's learned representations. And please note that this our learned salience map has some constraint. For example, this pixel value in the salience map has a range of 0 to 1. So 0 means no relevance, 1 means high relevance. And yeah, with respect to the explainability requirement we have in our method DIB-X, we introduce 3 requirements: minimality, sufficiency, and interactivity. So yes, the minimality requirement emphasizes presenting only the minimal explanation for understanding a model's decision. So it's a very simple, because if this explanation is very complex and long and lengthy, then it might not be able to be a good explanation. The good explanation should be very precise and very concrete. Here, the sufficiency requirement principle stresses that the learned explanation should remain consistent across the entirety of the data, ensuring sufficiently understandable. So this reflects the concept of self-explainability, because we don't want to create the one explanation per sample by every time at a time, but we just want to train the self-explainable system as a whole. So, and then we want the model to provide then some good explanation to the unseen data as well. And the third principle, interactivity principle, empowers users to understand explanations and leveraging their prior domain knowledge. I will come back to it a bit later, but I just want to focus on those two principles first, minimality and sufficiency principles. You probably found that they are a little bit contrasting to each other. In fact, this is true, and this contrasting, let's say, characteristics, the core idea of this so-called information bottleneck principle, which is very, very well established and very well studied lately. And yeah, I will come back to it a bit more later, very soon. So in DIB-X, what we are doing is the image test. So we are going to train a neural network for image classification in a supervised manner. But we modified the network architecture a little bit to additionally provide the explanation within a single downstream task. So we are doing the same image classification task, but we can get two outputs, prediction and then the saliency map. So yes, this is a simple illustrative figure for our framework. So this attribution mask M is our saliency map. As I mentioned before, this bright region should be close to 1. This dark region should close to 0. So yeah, if good explanation means that this attribution mask is properly highlighted with respect to the class label. So, and this bottleneck representation is quite important. So, this bottleneck representation T is computed by the element-wise product multiplication of this input X and this attribution mask M. So, if it's let's say this black region to be 0, then it will be masked out, left nothing. But if it's a region with the white, very bright, close to 1, then all the information in that region, which is hopefully this cute cat face, can be kept in the bottleneck representation. And then this classifier network try to classify this bottleneck representation only to given class information. So for this classifier network, it learns the mask M. So it contributes to mask M for sufficient information at bottleneck representation T. Because as you see, this is fixed information. This is also fixed information. All we can control is this mask M. And this bottleneck representation is also controlled by this mask M. So this classifier network try to learn the mask M for sufficient information at the bottleneck representation T. And this can be formulated by maximizing mutual information between this bottleneck representation T and this label Y. So yeah, maximize mutual information T and Y. On the other end, we have additional network called explainer network. It has an input and it creates some mask simply. And based on this mask, we create this bottleneck information. And based on this minimality principle, minimal explanation is a good explanation for this explainer network. So we don't want to include too much information to bottleneck, having all regions 1, so very, very white everywhere. Then it's not. Then this minimality is not let's say achieved here. So we want to minimize mutual information between X and T. So we want to discard as much as possible. This is sort of the goal for this explainer network. And then this is formulated by adding minus negative mutual information X and T to the objective function. So now what we can update is this attribution mask. But we feed by training this whole system end to end, we want to find some optimal balance between this minimality and sufficiency through this bottleneck information. And so, yes, as we saw, there's a trade-off relationship between sufficiency and minimality. And this is sort of the key idea to learn the optimal mask representation. So, in other words, we want to learn the mask as an explanation, which is include only minimally sufficient information. And here the beta is a hyperparameter that controls the balance. So this is we should manually tune these parameters. So yes, this is sort of the basic idea. Okay, then how to estimate these mutual information terms? In general, estimating mutual information is very, very difficult to compute because it requires marginal and joint distribution of these two variables. And we can, of course, and also we can rewrite this mutual information term by adding two marginal entropies substituted by their joint entropy. So in this case, let's say for the minimality principle between this original input X and this masked input T, they both are images. So and then it's very, very difficult to get their own true probability distribution because they have a very high dimensional data set, high dimensional representation. So we need a new measure to circumvent this issue. So we introduce a new measure, which is called matrix-based Rényi alpha order entropy functional, and it is grounded on this kernel method. And the final goal is to deterministically compute these entropies, marginal and joint entropies, based on this normalized gram matrix. So this gram matrix is it's like an affinity matrix. So you just create the sample-wise similarity with the given kernel, and the entropy in this with the new functional, the entropy of X can be computed based on its sum of these eigenvalues. And this is for marginal case. And for joint case, it's also simple because after applying some Hadamard product in between two gram matrices, and then compute the sum of the eigenvalues, and then add all of them, then it's equivalent to this joint entropy. It's a very, very handy approach compared to the previous method. So we use this deterministic information bottleneck method here. First, for the minimality term. Yeah, as I mentioned, this X is an original input and T is the masked input. And we want to, and this mutual information term can be split into these three entropy terms: marginal, and joint. And we have used those gram matrix-based the entropy functional, so we can compute this. For the sufficiency term, which is the mutual information between this bottleneck representation T and the Y, and there's a very nice property, so that by maximize, and it's equivalent to maximize this mutual information term, is to minimize this conditional entropy of Y given T, and this can be also approximated by the cross entropy term of this model prediction and label, true label. So yes, this is a whole objective function that we have for this setup. And in this, we want to learn this sufficiency minimality. We want to learn a good bottleneck representation, which is controlled by the mask, which is our salience map or explanation, using this sufficiency minimality trade-off. So, and I want to introduce one more explainability principle with a focus on users. So if this generated explanation is not very satisfactory in a specific domain, then what should we do? And in my opinion, a special request based on this domain knowledge can be provided into the form of this explanation. So then we can use those sort of prior or domain-specific knowledge in learning those good explanation. So I will say that good explanation should be interactive to the request. So, in order to achieve this sort of principle, we extend the objective function to enhance interactivity of our method DIB-X. So this is additional mask prior that we can, let's say for some reason, we can get those sort of masks, or we can learn that, yeah, all the cats has a very pointy ears. And then we can create those sort of pointy mask as a mask prior, and then we can incorporate the explanation. And of course, this is a very important prior knowledge. So this model, DIB-X model, will consider this mask prior in learning their good mask attribution mask. So we include this prior information mask prior, coupling with this mask, our learnable mask. We're using this Kullback library divergence measure. Here the gamma is additional hyperparameter that we need to tune. And this is a whole pipeline. So we have an X here, the input data image that is processed by the explain network to create some attribution mask M. And if there's a mask prior, it can couple within this mask attribution mask M, and this whole mask can be then coupled with this input again to create bottleneck representation T based on Hadamard product, and then classify by the classifier network to make some prediction, right? So this is summary about method DIB-X. So we introduced 3 different explainability principles and formulate them within information theoretical learning term. And the core mathematics or core idea is also relying on this matrix-based Rényi's alpha entropy functional, which is based on kernels and the pairwise relationship among the data samples to create gram matrix. And the sum of eigenvalues is equivalent to the entropy measure. Yeah, there are some figures that we create. So those are seal pups, hop seal pups, hooded seal pups. And this is the explanation that we get from our method. So for them, we don't use any prior information because we don't have it. And this mask has a single channel. So, but I'm very happy that they highlight the proper region. Another example is the multi-frequency Cossando data. And it's interesting because it has a 4 different, so every view, or when they collect the data in the same region, they send 4 different frequency channel, frequency acoustic waves. So low frequency to high frequency. And yes, and what we want is to create the mask with respect to each channels to see if there's any difference between the channels. Yes, So one of the advantages of this method is that we can freely define the form of this mask representation. And one thing interesting here is that within those marine acoustics domain, there is some prior knowledge that we can utilize, which is a cutoff intensity value of this raw input. So this is sort of the output, the mask prior that we create based on this conventional cutoff frequency intensity, cutoff intensity value. Yes, now moving on to our recent work, visually expandable document question answering. We present this work to NLDL as a poster. I took a picture with Dr. Muhammad Ali Soib Gui. He's from Spain. He's doing his postdoc there. But we also have a great collaborator, Kang-Soo Jung from INEA, France. And this document visual question is a task of answering questions about information present in the document images. So it requires some visual understanding with the textual reasoning. So it fits a multimodal setting. So this is an example of the data set. So we have some scanned image of this envelope, and there are some queries and answers. Yes, and of course, there are in those sort of method, there are two different directions, OCR dependent and OCR free. But we are now thinking about OCR free. Here, OCR is sort of optical character recognition. So if you scan the document, then it automatically take the text part and then give you like a digitalized text or vectorized text. So we have a base model which is called PIX2Struct. PIX2Struct. This paper is published 2 years ago in ICML, and it's about training. So, and they train this document image with those query questions to make some answer. So they provide the document image and query, and also they provide this bounding box like a mask. This is also given. They are sort of part of this visual information. And since it's a labeled data, it's a training. So what they want is to make a good answer. And of course, in this paper, there are some technical details, but I will not delve into more than that. And what we want is to make this docVQA self-explainable. And instead of using this given mask, like this bounding box, we want to make it learn within the system. So what we want is to make a right answer based on this document image only and this query without having this mask here. And then we apply this explainability principles in DIB-X, sufficiency, minimality, and interactivity. Yeah, yes. I don't think I need to do recap here. So, but I just want to briefly emphasize that the interactive principle is related to the human understandable reasoning based on this mask prior. And actually, it's very important in this docVQA setup, because when we train this model only with two principles, sufficiency, minimality, and this mask tend to be easily overfitted by highlighting only the answer region without any context. So for example, this is a question: what is the estimated budget of conducting analysis of decision makers, information target in research and development? And this is sort of the answer. And all of a sudden, the mask just only focus onto the numbers. And then this expression doesn't have any meaning for us, because the main reason to have this explanation is to use them as an evidence. But when they only overfit into this, then it doesn't make any sense. And it reduces this reliability of the explanations. So our remedy to this problem is to introduce an additional intelligence model. We couple with this another pre-trained model called ColPaly. And this cold poly model just highlights the patches that are relevant to the queries and answers. So they are based on the similarity scores. And it actually provides very noise mask, and this might need to be refined. And we can do this within our framework. So for example, this is the same document and the same answer. And when we just process this sort of query into the cold poly model, and it highlights something like this. So there are, some are relevant and some are not, but they are very noisy. So what we do is to incorporate this cold poly model as an prior information and optimize it through the whole network. So let me follow step by step. So we have a query and images feed into the network, into the pixel structure that we are going to train, and it has some masthead. So first, we just send through the masthead, we just run some mask information, where this mask information will be coupled with the code output from the cold poly model, which is additional mask, and then that takes this interactivity principles. And then this masked input, based on this mask, we make this masked input coupling with this input signal, and then feed into the pixel model again, and then with the text it, and we get some prediction. So here we get some sufficiency because we want some consistent self-explainable model. And here we still want to minimize information, minimal explanation. So we introduce this minimality term here. So yeah, I brought a few results. So this is a result without the interactivity principle. So actually, the question is, what is the budget offered for 3 posters? The answer is 27,000. It doesn't make a good prediction, but at least ours try to show very, very, let's say, stable mask with good accuracy. Another examples, but actually for this one, our model even make a wrong answer. The correct answer is official batch, but our answer said automation by official batch only. So, but still it's better than this setup. It just return some numbers without any clue. There are some quantitative results we have, still outperforming than the others. So yes, this is a bit. So yeah, we together with my colleagues, we publish our paper DIB-X, Formulating Explainability Principles for Self-Explainable Model through Information Theoretic Learning. So what we propose there is that it's a self-explainable model that learns from the explainability principles, sufficiency, minimality, and interactivity. And information theoretic approaches are chosen, for example, information bottleneck framework, and also Rényi's alpha entropy functional. And then we apply this DIB-X framework to this document VQA setting. So we make it, our aim is to make it a visually explainable document VQA. And we learn the mask to provide an evidence to answer to the query instead of providing bounding box like mask to the model. And also we want to keep those contextual information for a reliable explanation. And to achieve this, we introduce additional intelligence model called poly through the interactivity principle. So future works, we're making a full draft for this document, visually explainable document VQA paper. So for this region, this recording will be available after the work is published. And now we are trying our method into the different data set. For example, the graphical document data, where large tables or large diagrams or bar graph are included. And additionally, we try to incorporate this our framework with this other framework, for example, differential privacy. And then hopefully we can develop a new explainability principles through this collaboration. And personally, it's very interesting to do this project with the 3 different countries, Spain, France, and Norway. So yes, this is my last slide, and thank you for your attention. I'm happy to receive your questions.